are based on trees. Then there are certain kind of compression algorithm which we'll be seeing as an application or coding and decoding algorithm called as Huffman coding, which helps us in creating trees that save lot of data cost during the data transmission. Then there are something called as game trees, which are used for playing multiplayer games on the computer. So there are various applications of trees, and simply trees can be defined as graphs that do not contain circuits. Okay, trees are nothing but graphs which do not contain circuits. So a tree is basically a connected undirected graph with no simple circuits. So what is a tree? Tree is a connected undirected graph with no simple circuits. So it is connected undirected graph with no circuits. Now, for example, I'll draw a few trees here. Okay, so we can have, let's say, A, B, C, D, and E. So this is one. Okay. Then it should not have a circuit. That's the only requirement. So let us say A, B, C, D, E, F, and G. So there are no circuits here. So we can say that it is a tree. We can say it is a tree. Now I draw the same diagram again here. But understand the vertices A, B, C, D, E, and F. What is the difference between two successive diagrams here? The middle vertex is not existing. So in this case, this is not a tree, though it is overlapping. Okay, it is not a tree because the A, B, E, F is one component and DC is another component. So it has two components. So this is not a tree. This is called as forest. This is called as forest. There are two trees and this is called as a forest. If if the tree has, if the graph has a circuit, then it is not. The graph has, if a graph has a circuit, it is not a tree. For example, okay, so let us say A, B, C, D, and E. So there is a circuit in the graph, and so this is not a tree. Okay, this is not a tree. Let's move on further. Okay, now, as the definition says that tree is a connected undirected graph, tree is a connected undirected graph with simple circuits, okay, with no simple circuits. So what does this mean? What does this mean is that an undirected graph is a tree if and only if there is a path between any two vertices. There's a path between any two vertices. Now, let's move on further to a new definition. A rooted tree, okay, new definition. Rooted tree. Rooted tree. The rooted tree is a tree which, which has its one of the vertex designated as a root. Okay, one of the vertex is designated as root. One of the vertex is designated as root, and every edge is directed away from the root. Every edge is directed away from the root. Okay, every edge is directed away from the root. So for example, I'll draw one tree here. Okay, let's name it this as A, B, C, D, E, F, G, H. Okay, so this is a tree with root as A. Okay, this is a tree with root as A. Let's draw one more tree. Let's say A, B, C, D, E, F, and G. This is another tree. Again, the root is A. Okay, another the root is A. Okay. Now the part of the tree, say this part of the tree is called as subtree. Okay, let the whole tree is denoted by T. Okay, whole tree is denoted by T. Okay, then the red color part. Okay, red color part. Let us name it as T1. Okay, is called as subtree. Is called as of subtree, and root of the subtree is C. The root of the subtree is C. So T1 is subset of T, and T1 is called as subtree, and its root is at C. Similarly, I can say that in the next diagram or next of this tree encircled with brown, its root is, it is a subtree, and the root is D. Okay, the root is D. Okay. Now there are few more important aspects that I want to highlight here. The vertices like E, F, G, H, and I, or here F, G, E, C, are called as leaf vertices. What they are called as? Leaf. So leaf vertices, or they're also called as terminal vertices. Okay, they're also called as terminal vertices. So vertices which are at the end of the path are called as leaf vertices. They are called as leaf vertices. Now, now in the tree there is a parent and child relationship. So A is parent of B, C, and D. Okay, or B, C, and D are children of A. B, C, and D are siblings. So let's put them. So let us now draw one tree. I'm drawing bit bigger tree. Okay, so now let's name A, B, C, and D. E, F, G, H. Oh, sorry. E, F, G, I, J, K, L. L, M, N, and O. Let's say this is a tree. Now all the vertices, so every vertex here, for example, A has B, C, and D are children of A, and A is parent of B, C, and D. Similarly, B is parent of E and F. C is parent of G, H, I. D is parent of J, K, L. Okay. So just for an example, I'll write here parent and children. Okay. So A is parent of B, comma C, comma D. Okay, B comma C comma D. This is an example. E is parent of M and O. B is parent of E and F. C is parent of G, H, I, so on and so forth. Now, B, C, and D, I am circling them, are called as siblings. Okay, are called as siblings. So, vertices which are at same level and have a common parent are called as siblings. Similarly, E and F are siblings, G, H, I are siblings, J, K, L are siblings, M, N, O are siblings. Okay. So the vertices with the same parent are called as siblings. Now, B and A are called as ancestor of E. C and A are called as ancestor of G, H, and I. M's ancestors are E, B, and A. Okay, E, B, and A. So, the ancestors is nothing but the ancestor of a vertex other than root are the vertices in the path from the root to this vertex. So there's a path from A to M which comprises of A, B, E, A, B, E, M. So all the vertices other than M are called as ancestors of M. Okay, are called as ancestors of M. A vertex is called as leaf if it doesn't have any child. If it has no child, such vertices are called as leaf. The vertices which have at least one are called as internal vertices. Okay, internal vertices. So leaf and internal. Okay, leaves are also called as external vertices. So leaves are also called as internal vertices. Leaves are called as external vertices, and so in this case, M, N, O, F, G, H, I, J, K, L are leaf vertices, whereas E, B, C, D, E, B, C, D are internal vertices, as well as A is also an internal vertex. Okay, A is also an internal vertex. Now, any doubt up to this point? Now, a rooted tree is called as M array tree. M represents the branch factor. M array tree. So it's basic M array tree. If every internal vertex has no more than M children. So let me draw one tree so that we understand this. This is a tree. A, B, C, D, E, F, E, H, I, J, K, L, M, N, O, P, Q, R, S. Okay, now we look at the branch factor of the tree. The So at every node you can see the branch. For example, at G you can see the branch factor of 2. That is number of children it has. At B you can see the branch factor of 3. F, G and H. At A you can see the branch factor of 4. A, that is B, C, D and E are the children of A. So you have to consider if every internal, so a tree rooted at a rooted tree is called as M-array tree if every internal vertex has no more than M children. Okay, so this is 4-array tree. This is a 4-array tree because none of the internal vertex has more than 4 children. And in the curriculum, we'll maximum focus on M equal to 2, which is called a special class of M-array tree called as binary tree. Called as binary tree. So rooted trees with every vertex having no more than M children is called as M-array tree. So the tree above is called as 4-array tree. Okay, 4-array tree. So trees can be used. So we have seen so many applications of trees. Trees can be used to represent chemical components or chemical formula of, like for example, multiple uh, chemical compounds. Okay, trees can be used to represent organizational structures. Trees are used to represent a file structure or file system in the computers. Trees are used to indicate connected processors. So there are lot many properties of trees. Trees have a lot of applications in databases. Majority of the searching algorithms are based on trees. Bucketing or binning, that is tags in the social media network, are again based on trees. So trees have a lot of applications in the computer science domain. Now let's understand few properties of the tree before we move on. Trees have trees have paths, but they don't have circuits. So a tree with n vertices, a tree with a tree T, a tree T with n vertices, n vertices has n minus 1 edges. So it's very trivial. Okay, tree with n vertices has n minus 1 edges. Okay, so that's one. Then a M-array tree with I internal vertices. Okay, so let me introduce one more concept. A M-array tree. So what is M-array tree? That is the internal vertex doesn't have more than M children. But let me introduce one type of M-array tree. It's called as full M-array tree. Okay, full M-array tree. Now what is full M-array tree? If the vertex is internal vertex, all the internal vertices have fixed branch. Okay, so for example, if I say there's a 3-array tree, then every internal vertex has branch factor of 3. Okay, otherwise it is a leaf vertex. So who are the internal vertex? A, B, C, D, E, F, G, H, I, J. So in this case, A, B and D are internal vertices. C, E, F, G, H, I, J are external vertices or leaf vertices. So if the vertex is internal, it is having the branch factor to the fullest. Okay, compulsory all the internal vertex will have branch factor equal to m. So this is 3-ary tree. All the internal vertex have branch factor of 3. Okay, all the internal vertex have branch factor of 3. Now, if it is a full M-ary tree with I number of internal vertices, then total number of vertices are m of I plus 1. Okay, m of I plus 1. So how many internal vertices are there? Listen, there are 3 internal vertices here. So m is 3. 3 into 3 plus 1. Okay, that is 10. Count the number of vertices: A, B, C, D, 4, and lower 6. So 10. So if it is a M-ary tree, then the number of vertices are equal to m into I, where m is the branch max branch and I is the internal vertex. Okay. So then we get one more property, n is equal to mi plus 1. Then we have m raised to h, maximum number of leaves, m raised to h, maximum number of leaves in the M-ary tree of height h. In the M-ary tree of height h. So now the height of a tree is the maximum levels of the vertices. Okay. So height of a rooted tree is the length of the longest path from root to any vertex. So length of the longest path. So we have length of the longest path to be 2. A to B, B to E. So that's the 2. So height is length of the longest path. So m raised to h. So 3 raised to 2. So number of children possible is 3 raised to 2. H is equal to 2 and m is equal to 3. That is equal to 9. And you can see that B is having maximum number of children. D is also having maximum number. C doesn't have. But if we assume that C also has equal number of children, then the count comes out to be 9. Okay. The count comes out to be 9. Okay. So any doubts up to this point about the properties of the tree? So let's go to few more aspects before we close on for today. So as far as applications are concerned, there are a lot many applications for the tree. Search algorithms are applications of tree. When you're learning machine learning and data science, etc., you find many different algorithms which are tree based. Like for example, they are tree based. Then in the data structures, sorting algorithm which are based on divide and conquer method are also tree based. Trees are used again, tree structure like heaps is again used for searching in the databases. Trees are also used for the elements in the databases, so on and so forth. A very important application of trees is called as prefix coding. And the prefix coding is basically used to compress the length of the code, binary code, for the characters which are frequently used. And it is used to have longer codes for the characters which are rarely used. So that is basically prefix code. To generate those prefix codes, there's an algorithm called as Huffman coding. Okay, an algorithm called as Huffman coding. So what is basically a prefix code? So I'll draw here one small tree so that we can understand what is a prefix code. So let's put it. The left side of the tree is 0, 1, 0, 1, 0, 1, 0, 1. Okay. Now, at each terminal vertex, you have one of the element. Okay. What does this indicate? That E is most frequently used. So E's code is 0. A is used second. So A's code is 1, 0. Then I is used. So I's code is 1, 1, okay, 1, 1, 0. Now T's code is, let's say, 1, 1, 1, 0, and M's code is all ones. Okay, now what happens in traditional coding is that all the characters will have code of same length. For example, ASCII, all the characters have code of 8 bits. So even the characters which are most frequently used, they consume lot of memory because their frequency of occurrence is higher and the code length is fixed, and so they occur much space. But if a frequently occurring character, if its code length is smaller, then amount of energy, amount of space it will consume will also get decreased. So Huffman coding is called as variable length coding. ASCII is fixed coding. Prefix code is called as variable length coding. So characters which occur most frequently, they they have smaller codes, and characters which occur very rarely will have longer codes. Now, what is prefix in this? The prefix is that no bit string corresponds to more than one sequence of letter. Okay, so 1, 0, 1, 0 is not part of the first two bits of any of the code. Okay. Or 0 is not part of first bit of any of the code, so there's no confusion. If the code starts with 0, you can easily understand it's E. If it starts with 1 and ends with 0, you can understand it is easily A. If it starts with 1, 1, you are sure that it is neither E neither A. So this is called as prefix, and the overall coding mechanism is called as prefix coding. The prefix coding mechanism is variable length coding. Variable means each character will have a different code. Okay, each character will have a different code. So how does the prefix coding work? So we'll solve one problem here uh, to understand what is prefix coding. So write the problem. I expect everyone to solve it on the notebook. Use Huffman coding. Use Huffman coding. Use Huffman coding to to code the following symbols with given frequencies. So A's frequency is given to be 0.08. B's frequency, okay, it is given to be 0.1. C's frequency given to be 0.12. D's frequency is given to be 0.15. D is given to be 0.15. E's frequency is 0.2. E is 0.2 and F is 0.35. Now what is the requirement? The addition of frequency should be equal to 1. Okay, the addition of frequency should be equal to 1. So now let us solve this problem. So what is the first problem we have to do is we have to put the vertices initially and sort the vertices with their frequencies. A A, B, C, D, E, and F. Okay, so I'll sort them with the frequencies. Now combine the first two smallest frequencies and sort again with the frequencies. So if I combine first two, what is first two? So 0.08, 0.1, 0.12, 0.15, 0.2, and 0.35. So combine the two smallest. So A and B are the smallest. After assuming that the two are combined, sort them. So 0.1 plus 0.08 will be 0.18. So smallest will be C. So write C first. It is 0.12. Then D 0.15. Okay, then D 0.15. Now the combined of A and B, is 0.18. Okay, is 0.18, and write the bigger one on the left. Okay, so and A, B and A, 0 and 1, and this will be 0.18. 0.18. Again, E is 0.2 and F is 0.35. Again, combine the smallest one. So C and D will be the smallest one. Okay, C and D will be the smallest one. So as C and D are the smallest one, 0.15 plus 0.12 will become 0.27. So the first one will be 0.18 to come in the next step. So 0.18, which is B and A. Okay, its weight is 0.18. I'll write the weight now top. Then it will be E, whose weight is 0.2. Then it will be C and D. So D on the left, C. So this will be 0, 1. The total weight will be 0.27 and 0.35, which will be F. Now combine the two smallest one. So the two smallest one will be E, B, A, 0.2 and 0.18, E, B, A. So what will happen? So after combining these two, E and B, A together, 0.27 will be smallest. So write 0.27, D, C, 0.27. Then after 27, it will be F, which is 0.35, and the combination of E and B and A, 0, 1, 0, 1. So total will be 0.38. Okay, 0.38. Now combine the two smallest. Okay, combine the two smallest. I'll erase this part. Clear this. Combine the two smallest. So the two smallest that will be combined will be 0.27 and 0.35. So the combination will give me 0.38 E, 0, 1, B, 0, 1, and the other combination will be F, 0.62, and then D and C. Okay, 0, 1, 0, 1. Now combine the two smallest. Combine the two smallest. So we get a final tree here. 0, 1, the greater one on the left side. So it will be 0, 1, D, C, 0, 1, and this will be F. Same way. Here it will be E, 0, 1, B and A, 0 and 1. So what we get? We get A scored to be 1, 1, and the total of the tree was 1 at the top. We get B scored to be 1, 1, 0. C E scored to be 1, 0. Similarly, D scored to be D 0, 1, 0. C scored to be 0, 1, 1. And F scored to be 0, 0. Okay. Now what we can do is, if we take the bit length and multiply with the original frequencies, okay, to find average number of bits, find average number of bits, what we do, we take summation of summation of length of the code, okay, length of the code for symbol x into frequency of x. So in this case, it will be 3 into 0.08 plus B's code is also 3 into frequency of B. So it is 0.1 plus C, which is 3 into 0.12 plus D 3 into 0.15 plus E, which is 2 into 0.2 plus F 2 into 0.35. Okay, this, if you solve this, the average bit length will be happening to be, or is coming. So this is what is basically the Huffman coding.